Hello humans and welcome to another edition of our physics lectures. Tonight we're going to be talking about something called linear momentum. Momentum is something you've probably learned a lot about. We are going to be learning how it works in physics and doing a couple problems associated with it. Let's get started. So linear momentum is something that acts on bodies, on objects. So first thing that I want to do is define for ourselves something called the net force on an object, right? So we have an object here and there's forces pointing out in all directions. Now we know from studying forces that the net force on this object is sort of the sum of all the components of the forces acting on this object. And we also know that that is equal to ma. We learned this, of course, when we were talking about force. Now, it's not just any ma, it's a of the acceleration of the center of mass. Now, in our last lecture, we talked about center of mass, and that is the average position of all the masses in this object. And so the net forces equal the acceleration on specifically the center of mass. And in that lecture, in that video, we talked about how forces are always acting on this center of mass, or this object is experiencing forces at its center of mass. And so we're going to be focusing at this point. So we can almost think about this whole lumpy object as being just a point here at the center of mass. And so we can get this equation, which is something we're familiar with, F equals ma, but we can write it as F net. The net force, like if we add up all the forces together in their components, is equal to m times a at the center of mass. Okay, so we can do a thing with this. Now, so we've been talking about like forces and calculating them and calculating the accelerations that result, but what happens as time changes? What happens if we have forces that act, that start acting or stop acting or change with time? And so we can write a differential equation that defines force in terms of something changing over time. We know that this is something that we've done in the past for acceleration and velocity, written a differential equation to describe what one quantity is based on something else changing with time. So we're going to define this new quantity P. This new quantity P, we're going to say, as P is changing with time, we have a force. So we're going to make this new thing and say, if P changes with time, we get force. And we're going to call this P, this P is going to be called momentum, or linear momentum. Specifically, linear momentum. This P here is linear momentum. So we can solve this differential equation. We multiply the dt over to the other side. So this is a small amount of linear momentum, a small amount of time. We multiply the time to the other side. We get F net times dt. We get dp on the other side. We take the integral of both sides, and what we can do is we can plug in for this and say F net, right, is equal to ma center of mass, right? So we can plug in a center of mass here, ma center of mass. We can take the integral of ma, and we know that the integral of a is just v. So we get as a function of t. So a as a function of t, the integral of that is just v. And so we get integral of ma is just mv, the vector v, and that equals p. So we get this equation, p is equal to m times v. Okay, so if we define our force as having as the derivative of this quantity with respect to time, and we solve that differential equation, we get this as the result for what that quantity is equal to. And actually, interestingly enough, when you solve this in some special cases with relativity, this equation changes, but we're not going to deal with that right now. Maybe in another time. So we have this equation, P equals mv. Momentum, this P means momentum, it's called momentum, is equal to mass times velocity. And you can think of this in many different ways, kind of like the likelihood to be able to change motion based on a force being applied. But the key thing is that if there is a change in momentum, a force has been applied. So if P is not constant, if P changes, that means that there is some outside force being applied. Something is happening to change the momentum. The momentum will not change on its own. It will require an outside force. And this is an extension of like Newton's first law of motion, right? Where objects in motion stay in motion, and objects at rest stay at rest. And so this is an extension of that to say there's this quantity that's kind of check to see if things are staying the way they are or they're changing. And so if there's a change in P, that means that there is a force acting, that means there's an acceleration. It's all interlocked together, but momentum is a nice quantity for us to use. It'll actually make problems a little easier for us than just doing straight kinematics and then just doing straight forces. Okay, so if no force is applied, momentum must stay the same. It must stay the same. If no force is applied, the momentum will be constant. Okay, so what does that mean? There's a word that we use to describe that, and it is that momentum is conserved. That means that if no outside force is being applied, if it's a closed system with no outside force being applied, the initial momentum, the initial mass times velocity, is equal to the final momentum, the final mass times velocity. Okay, that's all momentum is really. It's saying that the initial momentum is equal to the final momentum if no force is applied. And we can use that to solve some problems. So let's start with it in one dimension. So here's momentum in one dimension, example of momentum in one dimension. So in this example, we've got a rocket ship with like a thing connected to the back of it. The total mass of the entire ship is M, capital M. And the little thing on the back is 20% of the total mass, so 0.2 M. It has some initial velocity. The whole thing together has some initial velocity, 2,100 meters per hour. Okay, and it's moving past like a sun. Okay, so this is the relative velocity in comparison to that sun. So there's some object in space. This thing is moving past it with a relative velocity of 2,100 meters per hour. The rocket ship then lets go of its thing behind it, right? And the relative speed, so if you're the sun observing this thing, you'll see that these two objects are moving with a difference of 500 meters per hour. Okay, so the difference between these two velocities, the velocity of B versus the velocity of A, is 500 units difference between these. Okay, we don't know the velocity of either of them. We just know that the relative velocity between them is 500. Okay, we want to find what is the velocity of our rocket ship after it's lost its payload. Okay, so we can write a thing to solve this. We can use momentum. First thing is to define the thing about the velocity, right? And that's just to say that the velocity of B is equal to the velocity of A minus 500. Okay, so basically saying that this thing is going 500 kilometers per hour slower, or is it kilometers? I'm realizing, it's kilometers. It's supposed to be a km. Okay. This thing is going 500 kilometers per hour slower than this one. And that's all this equation says, is that this one is going 500 slower than this one. All right. So that's our first little equation. That's just to help us understand the velocities of these two things and relate them together. Okay, so let's get into the momentum part, right? So momentum is conserved. It's conserved here. No external forces being acted. Okay, no external forces acting on this system at all. So we can say that the initial momentum is equal to the final momentum. And we know the initial momentum of this system, so this is the initial state, is the mass times its velocity. The total mass, M total mass, times the velocity, VI. Okay, so it's mass times velocity is the initial momentum. And that's going to be equal to the final momentum. So what is the final momentum? The final momentum is we have to add up the momentums of all of these parts. So the first part is this thing in the back. So it's 0.2 m times its velocity plus the thing in the front, 0.8 m times its velocity. Okay, so the final momentum is the momentum of each of these things. So again, momentum is mass times velocity. So mass times velocity and mass times velocity. We just add up for the final state. So the initial state has them together. The final state has them separate. But we just add up all the pieces to get the final momentum of this ship and thing, right? Because we need to have the whole system. We need to know what's happening in the entire system. Okay, so we can put some numbers into this. So we have it states it as mv initial, and then we get 0.2. We plug in from here. If we take this equation here, we plug it in for VB, right? So then if we plug that in there, then we get VA minus 500 m plus 0.8 m VA. We can cancel out all the m's. That's great. And then we get that. We basically get. It's going to be 0.2 VA plus 0.8 VA, which is just 1 VA. And then it's going to be minus 0.2 times 500. And then V1 over here is 2,100. Okay. So it's going to end up being, we can add that to 500 over the other side, 500 times 0.2, sorry, times here, and it's 2,100 plus 500 times 0.2, which this just becomes 100, and so it's 2,100 plus 100, and we get 2,200 kilometers per hour. And that gives us the velocity. And the way we were able to do this is because we knew that the initial momentum had to equal the final momentum of the system. Now, if we had removed this, if we had just ignored this for some reason, and like it jettisons it off, and then we accidentally forget about it, and just talk about the rocket ship, we would get the wrong answer. Because it's really important for us to remember all of the parts. All of the parts. We have to, if we start with an initial momentum of a system, we have to talk about what all of the parts do in the final scenario. This is very important. Okay, let's do another example problem. This is the same thing's gonna be true in this one. So this was in one dimension, right? It was just moving along the x-axis in one dimension. Let's switch it up and do it in 2 dimensions. All right, so here's my example in 2 dimensions. So my example is this. I've got like a disc thing, and in the center I've put like an explosive, all right? And the whole thing like blows apart, okay? So it starts just at rest, and then boom, it blows apart. And when it blows apart, the pieces go in different directions. So there's the A piece, the B piece, the C piece, and they go launching in different directions, okay? A launches that way, C launches this way, B launches that way, and there's an angle between each of the launches. And so these velocity vectors just tell you what direction they're going in, and the magnitude as always. Okay, we have some information about that. We know the mass of C, it's something. We have the velocity of C, it's also something. We have the mass of B, and we also have the mass of A. We don't know the velocities, though, of the other 2 pieces. Can we get them? We can, using momentum. So our first question is, what is the velocity of the B piece? Knowing just these things about the other pieces, the velocity of the C and all the masses, can we get the velocity of B? And we can. So let's check this. So if I redo this diagram in a slightly different way, this looks like I've crossed it out, but I'm not actually crossing it out. What's actually happening here is I have drawn the x-axis to be along the velocity vector of the A piece. So the A piece here, I've just drawn the x-axis to be parallel, actually just totally like overwriting the velocity vector in the a-axis. This is going to mean that I can cancel some stuff out, and I've chosen my y-axis to be in this like weird angle here. If I do a little bit of math, I can figure out what these angles would be to these axes. So we can do that now. So if I put a line through here, and I know that it's 100 degrees from here, from the A to the launch to the velocity angle of the C. If this is 100 degrees, I know that it's 180 all the way around, so it's 180 minus 100, which means that this angle will be 80, right? And I know that it's 130 degrees around to the B. It gives me that angle, 130 degrees. And so if I just take 80 away from 130, I'm left with 50. So I can get the angles of the 2 velocity vectors, the C velocity vector and the B velocity vector, with respect to this new x-axis, just by doing a little bit of simple geometry. And so this will be really nice. It's very convenient now because now there's no angle for the A, and it's also along the x-axis. This is going to make our lives simple, which is great. We want to always make our lives simple. So choosing our axes to eliminate one of the components is key. If we had put the axis like tilted off, we'd have to do way more calculations. All right, so what does this mean? So, okay, in momentum, just like every other thing we do in physics, we break stuff down into components. The stuff that happens in the x direction is orthogonal or doesn't interact with the stuff happening on the y-axis, right? So the momentum is conserved both on the x-axis and on the y-axis. The y momentum isn't going to mess with the x momentum, and the x momentum isn't going to mess with the y momentum. So we can talk about them separately. We can calculate the conservation of momentum both in the y direction and the x direction. All right, let's do that. So if we start writing some equations, let me shift this up, sorry. If we start writing some equations for this, we have that if we look at the momentum of A, block A in the y direction, there is no momentum The velocity in the y direction is 0. All the velocity is in the x direction. So the final momentum of the A piece is going to be 0 in the y direction. That's cool. What about for the other pieces? The momentum final for the B piece in the y direction is going to be, well, first of all, it's down, so it has to be minus because it's going to be a negative velocity, times the mass of the B piece, times the velocity, the final velocity of the B piece as well. So that's going to be equal to, in the y direction, that's equal to the mass times V final B. And as we always say, when you've got a component in the y direction, which trigonometric function do we use? Oh my God, yes, it's always sine. It's always sine. So we take the sine of the angle, and now we've got these convenient angles, so we can get the sine of that angle, so we can get the component in the y direction. So this will give us the component of the velocity in the y direction multiplied by the mass, negative sign because it's down. All right. Same thing for the C piece. If we want to get the y component, mass times velocity in the y direction, again we use sine because it's in the y direction, the sine of the angle to get that component there pointing in the y direction times the velocity vector. As always, we've got to multiply by the hypotenuse. We can't just slap a sign on things. It's not going to work. We need to scale it by the velocity vector. We make this mistake a lot where we forget to multiply by the hypotenuse. Don't forget to multiply by the hypotenuse. Otherwise, you will get really small numbers. But we want larger numbers because that's what we're given. Okay, so remember to multiply by this velocity. Remember always to multiply by the hypotenuse of your triangle. Key thing to remember, don't forget. All right, so well, here's the thing though. So we know that momentum is conserved. That means the initial momentum is equal to the total final momentum. If I add up all of these momentums, if I add up all these final momentums, this one, and this one, they should be equal to my initial momentum. But what is my initial momentum? Before the explosion happens, what is the velocity? 0. It's 0. My initial momentum is 0 for this whole thing. So I can add these all up and set them equal to 0 because this thing wasn't moving to start with. Some initial force was added, right? Some explosion happened and then velocity happened. There was a change in momentum of some kind, but it is conserved. Okay, so that's not the way to think about it. I'm sorry. So there was a thing happens. We go from no velocity to velocity in all directions, but it has to be conserved. So the velocities have to all add up, scaled by their masses, and we can do that by just adding them up and say them equal to 0. Initial momentum was 0. Final momentums are these three pieces here. So we have those things. We just calculated them. We can throw them into an equation. We can put them in here. We can do some rearrangement, and we get mc. So the mass of the C piece times the final velocity in the C direction, or the C piece times sine 180 minus the mass B times the velocity final in the B direction, or the B piece times sine 50. Now, of course, what we're looking for is this one here. All we've got to do is a rearrangement. We add that over to the other side. We divide by MB. We divide by sine 50. We're left with velocity final B. All these things are things we have. MC, 0.3 m. V, FC, 5. Sine 80, we have. MB, 0.5 m, or MB, 0.2 m. We don't have this one, sine 50 we have. You'll notice that the big M's, I was putting my finger up here, but I realized I wasn't showing. These are all numbers we have up here, but all the big M's are going to cancel because it's all equal to 0. It's all equal to 0. So those big M's will just cancel out, and we won't have to worry about the big M's, because when we plug M's in for these, we plug in for the big M's here, the big M's will cancel out of these because it's equal to 0. And we're left with a number. The V final is equal to 9.6 meters per second. But that was all just calculation. The key here is understanding that the sum of all the momentums in the final state is equal to the sum of all momentums in the initial state. And again, we're not leaving any pieces out. I know that we're talking about the B piece here, but we're not forgetting about the C piece, and we're not forgetting about the A piece. Even though the A piece was 0 in this particular case, we didn't forget about it. The other key was that we set our axes to make it easy for us so that the A piece would go to 0. That's what we wanted. So that made our lives a lot easier. All right, let's keep it going though. We can calculate a little bit more with this one. So here we've got, now we want to know, okay, what is the velocity in the A direction, right? We get the velocity in the B direction, but what is the velocity in the A direction? And so if this is the A direction here, let's take a look. Let's take a look at what we're going to see is going to happen. So first off, we know that initial is going to equal final, right? The momentum initial in the x direction has to equal the momentum final also in the x direction. That means that the final momentum has to plus of the A, final momentum of the B, final momentum of the C, all in the x direction have to equal 0. Because remember, it starts at rest. So the initial momentum was all 0. So let's take a look at what that would be. If we look back here, momentum in the x direction for the A piece is just mass times velocity because the A is already oriented on the x-axis. For these other ones, we're going to need the cosine component of each of their velocities because we're going to relate it to, we're going to add it up with this one as well. Okay, and we put the axes like this so that we could get this pointing in the x direction. So we didn't have to do any trig for the A component. All right, so to do that, we know that it's, first of all, it's in the negative direction, right, because it's moving backwards. Positive x was this way, positive y was that way, and so this is going to be negative, right? So we have a negative A mass times the final velocity of A, plus the B mass times the final velocity of B, plus the C mass times the final velocity of C, just like we might expect. Mass times velocity in each cases. Each of these just forms one of these, right? So the momentum of the A piece, momentum of the B, momentum in the C, all in the x direction, all the final momentums equal these. Mass times velocity, mass times velocity, mass times velocity, all added up together. The sign tells us the direction. The F means final. The letter tells us which version of it is. The X tells us which axis we're working on, and it's the x-axis. We could do this on the y-axis too, but if you notice from our example, there's no velocity for A in the y direction, so it's going to be really hard for us to figure out the velocity for A since there's none in the y direction. We just do it in the x direction. Okay, so we have that all up. We toss in some numbers. Again, it's all equal to 0, so the big M's all cancel out, just like before, and we're left with this. Here. We just calculated V final B. We were given V final C. The rest of them are just cosines of angles. We can rearrange that. It's all equal to 0, right? This is all equal to 0 because the initial momentum was 0. We can rearrange that and we get 3 meters per second. All right, that's the end. I hope you enjoyed. Momentum is pretty easy as long as you're equating all of the initial state to all of the final state. Don't forget to not leave anything out. And remember, choose your axes so you don't have to use as many trig functions. You will need to do trig functions to do this in 2 dimensions, of course, but you can choose your axes wisely to minimize the trig functions you used. See you next time. Bye.